the water was really bad tasting, but people didn't get it. Didn't get that this bad tasting water was the reason of the cholera. And then they started by, in order to solve the problem of the bad tasting water, what they did at the beginning was the result of a commercial operation. And this is another very interesting story. They suggested to mix water with wine. And in this way, they didn't kill the cholera, because it's not fermentation, it's something, it's just mixing. But they suggested it basically because they wanted to sell the wine. And this is another case. Sometimes we see that today there is a lot of speculation in the world. If you look back, this is another example of speculation. But then they realized, because they got the voice, they realized that they had to stop taking water from the underground. And then they thought how to get the water then to feed Bologna. And they had memories, very far memories, of the Romans taking water from the hills. And therefore they started exploring, and they found the Roman aqueduct. It was a gallery, and this gallery is still be used by Bologna to take part of its water. And it's a gallery that starts from the hills, over the hills, and brings water to Bologna. It's digged into rock, and it was recovered in the 1700 after like 1,000 years of not use. So it's very interesting. Anyway, if we, let me go back now to the problem of water resources assessment and rivers. I'm looking at the picture, the page to see if I'm not forgetting anything. Rivers. Okay, you have a time series then. Okay, you have an hydrograph. How to quantify water resources availability. There is a graphical method that is still largely used. And don't underestimate the power of graphical methods, because they were used in the past because they didn't have the PC, and therefore they used graphics in order to make computations with graphical integration. You may have heard about that. But graphical methods have a very good convincing power, and in water resources management we need to take care about convincing power. So, this graphical method, which I want to talk to you about, and I anticipate that we will make an exercise on it. So I have no doubt that you will understand how to use it, no doubt, okay? And as I lecture it, you may have some doubts, but the exercise will clarify everything. So, I'm talking about the flow duration curve. Good. Is this term already known to some of you? Okay, you and you, just a couple of people. Okay, so you will need to be a little bit patient. I will rush a little bit, so the others will be patient because I'm rushing a little bit. But we will make an exercise. Okay, so what is the flow duration curve? Let's suppose that you have an hydrograph that lasts for 1 year. Okay? And before providing you the definition of the flow duration curve, I tell you an easy way to compute it. It's a reverse approach, it's an inductive approach that I think it's clear. So you have an hydrograph of 1 year. Let me show you. I think it's useless that let me use this one. Okay, this is an hydrograph. Let's suppose that it's 1 year, okay, with 2 peaks, 2 high flow periods. Just look at the hydrograph for now, and just look at this, okay, on the left-hand side. Stream flow time, as I said, 1 year. Okay, good. Now, the question is, let me identify a river flow, and let me identify the percentage of time that river flow was equaled or exceeded. Again, let me identify a river flow. The river flow is like A. Okay? Let me identify the percentage of time. I say again, the river flow was equaled or exceeded. The question is very relevant because let's suppose that I am interested in getting this river flow A from the river. And the question is, how long can I take it? I can take it only if the flow in the river is equal or higher. So it's very relevant, the question. Okay, let's define a river flow A. What is the percentage of time the river flow is equaled or exceeded? Because it means that for that percentage of time I can take it from the river. Let's forget about environmental flow requirements. Let's forget about any other restriction for now. The only restriction I'm considering is availability. Okay, so if I take the river flow A, you see the red line is the length of time. The river flow was equaled or exceeded. Good. Let me bring it on another graph here, where I have again stream flow here, and in the abscissa I have duration. This is the flow duration curve. So A, river flow A, the duration is given by the red line. You can express the duration in relative form, so the percentage of time, or in absolute terms, like number of days. It's equivalent. I like to introduce it by thinking of percentage. Good. So here you see duration. It's not specified if it is a percentage or if it's a time duration. Good. Let me take a lower river flow, B. I'm expecting that the duration is longer, because if I lower the threshold, duration is longer. In fact, I see two segments now, B plus C. I sum them here. Let me take the lowest flow D. Duration is extended over the whole here. This is the flow duration curve. I didn't define it, but I think it's clear how it's derived. And let me just note that I made reference to 1 year only for now. If you want to study, of course, interannual variability, you need more years. So the next step is how to compute it if I have more years. I anticipate that one trivial reply is the extension of this method. Instead of plotting just 1 year, I plot here the whole collection of years, and I depict the flow duration curve in the same way. And the percentage, the duration, expressed in percentage, will be the percentage of 10 years, 5 years, 100 years, no problem. So let me show you, and then I close, a flow duration curve. I'm not sure if I have here on the web. Let's see if flow duration curve for river. Let me see if I can find a flow duration curve for the Po River. Let me see. I don't think so. Meaning that for river it's not easy because here we are international. Or let me make another attempt. Otherwise, I take a generic river, no problem. Sorry. I need to search in Italian because it was a trivial mistake. Let me see if Anyway, here is an example of a flow duration curve. Just 1 second. It's not of the Po River. I can see it. I don't think it's for the Po River. I'm not really sure. If you look at this picture, it's duration. It's here. It's there is written durata, which is the Italian translation for duration. It's expressed in days, 365, and here you have the river flow. In cubic meters per second. The unit of river flow is volume over time, and usually when we talk about rivers, it's cubic meters per second. And I'm saying that it's not for the Po River because 4,000 is too low for the Po River, unless it is a specific year. If it is just 1 year with not high flow, no high flows, it may be, but I'm not really sure. But and also there is another issue. It goes down too quickly for being a flow duration curve of the Po River. From the flow duration curve, you understand a lot of the river regime. And if it goes down so quickly, it means a lot of seasonal variability. And instead we have some curves that go down with a lower slope, and therefore it means less variability. Okay, now if some of you, I go back to my original question, if some of you have problems in getting, in following the forum, and